Hello friends, in this video we will study the branching instructions available in the instruction set of 8085 microprocessors. These branching instructions, they break the sequence of execution of instructions in the microprocessor, and they cause the microprocessor to jump to some other memory location. So they are breaking the branch, and they are making the microprocessor to execute some sub branch of the main program. So let us start with our topic. The branching instructions in 8085, in this category we are having three instructions: call, return and jump. Now this branching instructions means that suppose the microprocessor, it is executing the main program. Okay, now how the microprocessor execute any instruction? First it is going to fetch that instruction, then it is going to decode that instruction, and then it is going to execute that instruction. Okay, so this is the complete working of the 8085 microprocessor, how it runs the whole program. So suppose in the main program we have written different instructions, and at one position we have written any of the branching instructions. So what these branching instruction does, they shift the execution of the main program, or they break the sequence. Like suppose in this way, in this manner, line by line the microprocessor is executing the instructions. Suppose we have written the instruction call in between that main program. So after this call, other instructions are also written in the main program. So when the microprocessor, it executes this instruction call, then this instruction call, it breaks the sequence and it makes the microprocessor to jump to some other memory location where some instructions are written, and we can say that this is our main program and this is our sub program, and this sub program is written at some other memory locations other than this main program. Okay, so call means that it is calling that sub program to be executed by the microprocessor. So microprocessor, it breaks its sequence and it shifts to some other memory location or jump to some other memory location where that sub program is written. It is going to execute the instructions of that sub program and return back to the main program. It will return back to the next instruction after that branch instruction, means here we are using the call. So the next instruction after the call instruction, that is going to be executed by the microprocessor, and again the microprocessor resumes the execution of the main program. So because it is having a branch of the main program, that is why these instructions are called branching instructions. Okay, now here in these instructions we have two types. One is conditional and second is unconditional. Conditional means that this branching of the program will be done only when some condition is said to be true. Means when that condition is true, or when that condition is satisfied, only then the microprocessor is going to jump to some other memory location. If the condition is not satisfied, it is not going to jump, it will resume the instructions, or it is going to continue the execution of the other instructions. Okay, unconditional means no condition is specified. If that instruction is written in the main program, then microprocessor has to jump to some other memory location. So conditional, when condition is satisfied, only then microprocessor will jump. Unconditional, microprocessor has to jump in any situation. Okay, So let's start with these branching instructions called return and jump. First, we will start with the unconditional jump instruction. Jump unconditionally. The mnemonic for this is, mnemonic is the form in which the instruction is written in the program. So in the program, we are going to write JMP. And this instruction means that microprocessor has to jump, and there is no condition specified in the instruction. Now after this jump instruction, a 16-bit address is specified, because if the microprocessor has to shift to some other memory location, we have to specify the address of that memory location. So that address is specified in the instruction. 16-bit address will be the operand in this instruction. So what this instruction is doing, the program sequence is transferred. So the program sequence is transferred to the memory location specified by the 16-bit address which is present in the instruction. Okay. Example of this instruction are, let's suppose we are writing jump 2034. Okay, so microprocessor will jump to the memory location 2034, and whatever instructions are written at that memory location, that will be executed by the microprocessor. Now when the microprocessor is jumping to some other memory location, it has to come back to the main program also, so that the remaining instructions of the program, they can be executed. So whatever instruction is written after this jump instruction, suppose that move A comma C is written. Okay, so the address of this next instruction, that will be stored in the stack, so that when the microprocessor is coming back from the 2034 memory location, it has to come back to execute this move A comma C. So it can get the address of this next instruction from the stack. So in this way, microprocessor works whenever these branching instructions are written. It is going to store the address of the next memory location in the stack, so that it can resume back the execution of the main program. Now this was jump unconditionally. There is another instruction which is the jump conditional. Okay, and in that condition will be specified, and that condition, if that condition is satisfied, only then the jumping will be performed. So second instruction is jump conditionally. Now because in this instruction we have to specify the conditions, so there are various types of jump conditional instructions, and in that we are using the flags of the 8085 microprocessor. In 8085 we are having different flags like sign, zero, parity, carry, auxiliary carry. So out of these flags, any of the flags can be used to form the jump conditional instruction. The examples of these instructions are JC, JNC, JP, JM, JZ, JNZ, JPE and JPO. So these jump instructions, they are using the various flags of the 8085 microprocessor. Like JC means jump on carry, means whenever the carry flag is set, it is going to jump. If the carry flag, value of the carry flag is 1 and it is set, then only microprocessor is going to jump to the other memory location. So JC means jump on carry. And for that, carry flag has to be 1. Okay. JNC means jump on no carry. No carry means no carry has to be generated, so carry flag will be 0 in this case. Okay. Carry flag is 1 means it is set, and carry flag is 0 means it is reset. Then we are having JP means jump on positive. It means the number, if the number is a positive number, then it is going to jump to the other memory location. Now positive and negative number, they are shown by the sign flag. So if the sign flag is 0, then it is going to jump. Okay. And JP means jump on minus. Means if the number is a negative number. A negative number when the sign flag is 1. Then we are having jump on 0 means when the 0 flag is 1. Means if the result of any arithmetic and logical operation, if we are obtaining it as 0, then the 0 flag is set to 1. So if the value of 0 flag is 1, then it is going to jump to other memory location. Then jump on no 0 means 0 flag is reset, 0. JPE means jump on parity, even. If the parity is even, then the parity flag is set to 1. If the parity is odd, jump on parity, odd. Then parity flag is 0. Okay. So these are the conditional jump instructions which are using the various conditions, and when those conditions are satisfied, then the program sequence is transferred to some other memory location, and the address will be specified in the instruction itself. After these conditions, a 16-bit address will be specified. So we can say that the mnemonic for this will become J, and the condition is carry, no carry, positive, minus, 0, no 0, parity even, and parity odd. These are the conditions. So J will be written, then condition will be specified, and then the 16-bit address will be written. So when that condition is specified, then microprocessor program sequence is transferred to that memory location. Okay. Example of this is jump on carry 2034. So when the carry flag is set to 1, then it is going to jump at the memory location 2034. Okay. Here also, when the microprocessor is jumping to that memory location, so the address of the next instruction after this jump, that will be stored in the stack, so that the microprocessor, when it is coming back from the execution of the sub program, if it is coming back to the main program, then it can resume back its execution by getting the address of the next instruction from the stack. Okay. Next branching instruction is the call instruction. Now in the microprocessor, we have a term subroutine. Subroutine term is given to a short program which is written at some other memory location other than the main program. So earlier I have said that in the main program, if we are using the call instruction or jump instruction, microprocessor has to jump to some other memory location to execute a sub program or a short program, and that sub program or that short program is given the term subroutine in the microprocessor. So here we are having the unconditional subroutine call as our next branch instruction, and the mnemonic for this is call and the 16-bit address. So when this instruction is written in the microprocessor, in the main program, then the microprocessor jump to the 16-bit memory location, address of that memory location, it is going to jump and then execute that subroutine. Okay. So the program sequence is transferred to the memory location specified by the 16-bit address which is in the instruction itself. Now before the transfer of the program sequence is done, then the instruction which is written after the call instruction, the address of that next instruction will be stored in the stack using the push instruction. Okay, so the address of the next instruction will be stored in the stack. Let's take an example here. Suppose we are writing call 2034. Okay, and we have earlier our main program, we have various instructions above this call, and after the call we are also having some other instructions. Now in the main program we have used this instruction called 2034. Now suppose this main program, it is written at some memory location, so like from 8000 the program has been written in the memory. Okay, and this instruction called 2034, it is written as 8021 memory location. Okay, now the instruction after this call is suppose move a comma c. Okay, and this instruction is written at the memory location 8024. Okay, because call instruction, it is a 3-byte instruction. For call we will have a machine code, and for 20 we are going to use one memory location, and for 34 we are going to use one memory location. So it is a 3-byte instruction. So next instruction will be written at the memory location 8024. Now when the microprocessor executes this call instruction, it is going to jump at the memory location 2034 where some subroutine is written. So microprocessor has to execute this subroutine. Okay, and in this subroutine we are having different instructions. Now when the microprocessor has completely executed this subroutine, it has to return back to the memory location where the move a comma c next instruction after the call is written, so that it can resume back the execution of the main program. So how the microprocessor is getting that? When the microprocessor is executing this call instruction, it is going to store the address of the next instruction in the stack. So stack, it is the set of memory locations which are used for temporary storage of data. Now stack is initialized by the stack pointer SP, and suppose at some memory location we have initialized the stack pointer like suppose 9024. Okay, there we have initialized the stack. Now we have to store the address of the next instruction. So first the instruction will be the address will be stored here. So stack pointer will be decremented by 1. Okay, so it is 9024, it will become 9023. Okay, and then we are going to store the address over here. So 24 is stored, and then again the stack pointer is decremented by 1 because now the stack pointer will come to this position. We have decremented it, it will become 9024. Again it is going to be decremented, it will become 9022. Okay, so then the next higher order address will be stored. Now when the microprocessor is coming back after the execution of the subroutine, it is going to pop the address from the stack it will get 8024, and there it is going to execute the other instructions of the main program. So this is how the call instructions and branching instructions they are executed. The next instruction, address of the next instruction, that will be stored in the stack using the push instruction, and when we are getting back the address we will use the pop instruction. Okay. So this call instruction, it was an unconditional call instruction. There is no condition specified here. Whenever these instructions are written, microprocessor has to jump to this memory location and execute the subroutine. There are other instructions also, like the conditional call instructions. Call conditionally. So here some condition will be specified, and when that condition is satisfied, only then the microprocessor will jump to the memory location. So the mnemonic will become, we will have C, okay, C for the call, then condition will be written, and then the 16-bit address. Now here also for the condition we are going to use, or the microprocessor uses the flags, okay, flags like sign, zero, parity, and the auxiliary carry. So based on that we are having different conditional call instructions like CC, CNC, CP, CM, CNZ, CZ, CPE, and CPO. Again, like call on carry, call on no carry, call on positive, call on minus, call on no zero, call on zero, call on parity even, and call on parity odd. So all these conditional call instructions, they are based on the conditions on the carry flag, on the sign flag, on zero flag, and on the parity flag. Okay. So when that condition is specified, then it is going to jump to that 16-bit address memory location and then execute that subroutine. So there were two call instructions, unconditional call and conditional call instruction. Next we are having the return instruction. Now in return also we are having two types of return instruction, return unconditionally and return conditionally. Return from subroutine unconditionally means we are not going to specify any of the conditions, and mnemonic for this will be only RET. Okay, no operand has to be specified, no address has to be specified, because when the microprocessor is returning back from the subroutine, it is getting the address from the stack. So there is no need to specify the address in the instruction. We are just going to write the RET. So due to this instruction, the program sequence is transferred from the subroutine to the main program or the instruction which is written after the call instruction. Okay. Now when this return instruction is executed, the stack, it is popped up, the contents of the stack, they are popped two times. First we will get the higher order address and then we will get the lower order address. So complete 16-bit address will be available to us from the stack, and the microprocessor can return back to the main program through this instruction. Example of this is, we are just writing RET. Okay. So here no condition is specified, so it is an unconditional return instruction. Another type of return instruction is return from subroutine conditionally. So here some condition will be specified in the instruction, and when that condition is satisfied, then microprocessor will return to the main program or return from the subroutine. So mnemonic will become R and then the condition, okay, and no operand is specified again, just we are writing the R and the condition. So again for the condition, the flags are used like return on carry, return on no carry, return on positive, return on minus, return on zero, return on non-zero, and return on parity even, and return on parity odd. So here R is for the return instruction and then the conditions are specified. Okay, and when that conditions are satisfied, then the microprocessor will return from the subroutine to the main program. Again, it is getting the address of the next instruction from the stack. It is going to pop the contents of the stack and it will get the complete 16-bit address of the instruction of the next instruction, from where it has to resume back the execution of the main program. So these were the branching instructions which are breaking the sequence of the main program and transferring it control to some other memory location where the subprogram or the subroutine is written. And this jumping of the program or branching of the program, it can be conditionally or it can be unconditionally. Okay, so we are having three instructions: jump, call and return, and all these three instructions, they are having two types based on the unconditional and the conditional situation. So I hope that this topic, branching instructions in 8085 microprocessor, it is clear to you. Thank you.